Welcome to this online informational session about the Resilient Together Collins Cove Park Neighborhood Project. I'm Neil Duffy, Director of Sustainability and Resiliency for the City of Salem. We don't have a lot of attendees present right now, but I just want to make sure people know if you're watching this recording after the fact that there is a Spanish recorded version. There is interpretation available tonight, so there is a Spanish version available, likely on the same public input page where you're watching this video. Um, so um, we can go to the next slide, please, Christian. So tonight we're going to be speaking about the Collins Cove Park neighborhood mitigation project. We'll do some introductions about the team and the project. We're going to be providing project updates both on the coastal preliminary design and concepts, as well as the stormwater preliminary designs and concepts, and also provide some information on some groundwater analysis that was done as part of this project, and talk some about the next steps for this work. Next slide, please. So just briefly, this is the project team. I introduced myself already. Christian Team is a resilience project manager in our department. We've also been working with Barbara Warren Environmental Consulting and Salem Sound Coast Watch, both on project management and a lot of the outreach and engagement with the community, as well as the team from AECOM, Matt Delp, coastal engineer, and Helen Douglas, senior civil and project manager, are joining us tonight to speak about the work that they've been doing. Tyler Brinson's also been a valuable member of the team, especially on the stormwater side, but he's not here tonight. Next page, next slide, please. So just a little bit of a refresher if people are familiar with the project and some background. This is a project that's funded by Massachusetts Coastal Zone Management. It's a 2-year grant that the city received, and we're winding up the second year of that grant process. And it was to study mitigation alternatives in the Collins Cove Park neighborhood area. You'll see that yellow boundary is the project area that was really the focus of the study. That red area, that red outline, was a study area boundary for a Collins Cove to Willow study that was conducted, also funded by the state MVP program prior to this study, which studied the flood risks in that whole wide swath. And then, as a result of that study, we wanted to explore. This was one of the priority areas identified, and so we've been pursuing different solutions in the Collins Cove Park neighborhood area. Next slide, I think, and I think I'll be handing it over to Matt at this point.
All right, thanks, Neil. Good evening, everyone. I'm Matt Delp. I'm a coastal engineer with.
Oh, Matt, sorry, quickly.
Oh, yeah.
Just for those attending, if you do have questions, please use the Q&A function, and we can either try to answer them in real time or and pause at the end and answer them then. So thanks. Sorry.
Sure. Yeah, no problem. So I'll be talking about the coastal flooding analysis that we completed as part of this project, which, composed of analyzing coastal flooding in the system and then developing some different mitigation alternatives and coming up with a preliminary design for a preferred alternative. So I'll be talking about coastal flooding first, and then I'll be talking about stormwater flooding, which is another type of flooding that the neighborhood experiences and deals with as an issue. But like I mentioned in this first part, I'll just be focusing on the coastal flooding aspect in the neighborhood. Next slide. So here are some example images of a storm back in December of 2022, where coastal floodwaters from a significant storm surge um, that occurred during a high tide overtopped the existing seawall and started to flood the park behind it. So in the images on the left, you can see um, one of the flood pathways that we actually looked at as part of this project, where water starts to come over the wall and floods in between the playground and ball court. On the right is an image of the southern side of the park near the near Collins Cove, along Collins Cove Beach, where floodwaters were just about at the top of the seawall. And then in the lower right is an image of the end of Connors Road, where coastal floodwaters did overtop the existing wall and started to flood some of Connors Road behind it. Next slide. And so, in addition to this kind of anecdotal evidence of coastal flooding that's been happening in this area, we also simulated flooding using some coastal models to look at what present day major storm flooding impacts are. So that image on the left shows um, flood depths for a major storm, and the image on the right shows um, major storm event with sea level rise included and what those flood depths might look like in the neighborhood. So there's fairly extensive flooding back behind the park and starting to get into the neighborhood for that present day major storm. But with those sea level rise impacts as well, that flooding is exacerbated even more, and there's much more extensive flooding back in the neighborhood. Um, and so we looked at this. We looked at this flooding from um, coastal modeling perspective earlier on in the project, um, and that helped us figure out, what types of projects or what was needed to try to protect the park in the neighborhood and mitigate for flooding from these types of storms. Next slide. Um, so, you know, assuming most you all are familiar with the park, there is an existing seawall along the entire perimeter of the park, but something that you may have noticed is that there's a number of different sections or um, types of wall. Um, and at the bottom of the slide, um, we've listed out um, those 8 different sections of wall, um, some of which are um, public structures, which are labeled in green, and then the blue one, and private structures are labeled in blue. Um, each section of wall is in varying condition, um, some of which are in significant need of repair work, notably sections 4, 5, and 7, um, in which um, some of the foundation are starting to, um, where there's been a loss of foundation along some sections of uh, seawall 4, and then 5 and 7, where some of the existing stone is starting to break down and um, and the wall is currently failing. Next slide. So as we started to consider what types of projects um, we could evaluate to mitigate the flooding in the park, we also considered, where would the flood barrier be? Would um, and we're showing 2 of those examples in this slide with a possible alignment that follows more or less the back end of the park, which we call the road alignment. And so you can see, where that alignment that we looked at would follow along that back edge of the park on the left-hand side. And then we also looked at um, an alignment that follows the shoreline. And ultimately, we found that both options would be similar in construction cost and both serve the same purpose of protecting the neighborhood. But the value of following the shoreline is that it would um, minimize maintenance costs for restoring the park. After future flooding in which there's potential like damage or cleanup of the park. Um, Having protection of the park would reduce those maintenance costs, um, and also just would make it easier for the city to maintain that park. And During our last meeting, we had a survey for those who attended to indicate preference between different alignment options, and there was general consensus that the shoreline alignment was the preferred option for folks that attended. Next slide. So in addition to different alignments, we also evaluated different um, and compared different types of flood barriers. So some of those different types included a grass berm, pile supported wall, um, or just different types of walls that are structurally supported by either piles or sheet pile. Um, and then we also considered as an alternative to replace the existing seawall um, completely. Um, and ultimately, after going through the alternatives analysis, we ended up coming up with sort of a hybrid solution. And that's summarized on the next slide. So the preferred option, which we went with, was just based on some of the feedback that we've received from the community engagement, as well as talking with the Parks Department with the city, was having a vertical wall about 2 to 4 feet tall along that follows the shoreline, just landward of the existing seawall, um, and um, also including repair work for that existing seawall out in front of this new flood barrier. And so, like I mentioned, it would be around 2 to 4 feet tall. This elevation would be similar to the section of wall along Collins Cove Beach. And so, the elevation would match, and it would have a similar aesthetic to that wall. Also want to note that with the project, beach access would be maintained. Right now, we're considering having 4 different entrances to the beach, and so that would be those would be included along that same staircase in Collins Cove Beach.
Next slide, next slide.
Someone say next slide. Oh wait, sorry, I wasn't finished going through that summary slide. Yeah. And so, I'll talk more about the beach access in a later slide, but just I'll just wrap things up talking about the overall project with some cost estimating that was completed, which found the project to be roughly around 3.3 to $3 to $6 million. Next slide. So here's an overall concept site plan engineering drawing for the project. Um, I know it's a little challenging to read at this scale, but I just wanted to give a sense of the extent of where the project is. Um, so, like I mentioned, it would follow the flood barrier portion of the project would follow the shoreline portion of the park, um, starting at that southern corner, um, and wrap all the way around to the end of Connors Road. And I'll be in the next couple slides, I'll show some more detailed, um, higher resolution images of this drawing. But this is just to give a sense of the overall project. Next slide.
Hey, Matt, I just want to jump in and
Yep.
emphasize that, especially since we're looking at some of these schematic drawings, that this is a preferred concept, but we're still very much in the conceptual stage. So people who are watching this may get the sense that a lot of these decisions have been made, or a lot of specific design details um, have been nailed down, and that's not the case. So but these are. So I just wanted to make sure we emphasize that as we move forward. Thanks. Sorry.
Yeah, no, that's a good point. So yeah, keyword on that last slide header was conceptual or concept. Um, so yeah, as part of this process, we narrowed down more or less what the preferred wall type was and the position of it, but a lot of the finer details, design details, are um, still going to be evaluated during a more detailed design phase. So there's still a lot of opportunity to engage with the project and provide feedback to help progress it as it moves forward. Um, so here's one of these close-up images starting at the northern end of the project, along at the end of Connors Road. Um, I will note that there's also another section which you can see in the lower left-hand corner of the slide, at the end of Osgood Street, where we're suggesting a similar type of wall replacement, um, to um, to raise that portion of the wall, um, and try to mitigate for flooding at that location as well. But just since that's a smaller section, I didn't have its own. It doesn't have its own slide, but wanted to make sure to note that Osgood Street would also um, have a similar type of project or similar type of wall. Um, so along Connors Road, um, the wall would start um, at the end of Connors Road, where that wood guardrail is, and along this section of the wall, um, the project will actually be replacing the um, the existing seawall that's there. So, um, in terms of the position or the alignment of the wall, along this section, the wall would just follow the position of the existing wall itself, and you can imagine it being about 2 to 4 feet taller than the wall that exists out there now. It's comparable for those who have been down to this end of the park um, during the late fall, winter, early spring months, and saw some temporary sandbags um, protecting the road from flooding. The wall that we're suggesting as part of this conceptual design would be comparable to the elevation of those sandbags, just to give you a sense of the height of the wall. Um, and then so moving south along the wall, um, right around the middle of the screen, the wall actually tucks inwards, or tucks in landwards closer to Connors Road, where it starts to go straight. Um, and around this point, it will we're proposing um, to restore some additional beach area out in front of the wall, um, as well as provide access, which you can see on the left hand side of the screen, where there's an access point, and then um, some sort of ramp or staircase could be included to allow for people to walk down to that expanded beach area. Um, and then on the opposite side, there will also be a similar um, access point, um, which I'll explain in the next slide what that access might look like, um, and seasonally how it would be open for people to use. Um, but yeah, so this area would include an expanded beach area, and then have those two access points. Um, and right around the left-hand side of the screen, that's where the wall would likely um, be set back from the existing seawall. So most of the wall on this screen would become the new seawall, but right around the left-hand side of the screen right now, that's when the flood wall would transition to be set back from the existing seawall. Next slide. So like I mentioned, along those two access points, there are going to be two access points to the beach at that end near Connors Road, and then there are going to be two access points with this conceptual design um, to Collins Cove Beach. And um, along those access points, there are going to be something that looks like the what's called a deployable barrier. It's or called stop logs for that example in the upper right hand corner of the screen. Um, and what this type of design allows for is for access when those slats are open, and then in the city can then close those gates either before a storm or seasonally, at the end of the fall before the winter. Um, and so that would allow for protection of the neighborhood during major storm events, but then also provide access to the beach area in the spring, summer, or early fall months when people are trying to access the beach. Um, Next slide. And so jumping back to these design drawings around the middle of the park, um, so this is where you can see where that existing seawall um, would remain with that repair work. And this flood wall that we're proposing would be set back landward of that existing seawall, um, anywhere from what we're looking at now, around 2 to 6 feet, just based on some preliminary investigations of the soil and the depth of any like stone or seawall beneath those areas. Um, so some of those investigations into the soils would tell us how far back that wall can be from the existing wall. And just for a reference point, something that came up on a walk and talk that we had recently was the distance between the stands for the ball field, which you can see kind of on the lower left hand corner of the screen. Just for a reference, the distance from the stands to the existing back of the existing seawall is around 10 feet. And we're thinking right now it looks like in this graphic that the wall is very close to the stands. We're thinking it would land probably somewhere roughly in between. So if we're saying it's 10 feet between the stands and the existing wall, it would be about 5 feet between either end. Um, just to give a little reference of where that would be. Um, and then, as both I and Neil have mentioned, this is very much in a conceptual design phase. Um, Something that could be included in future iterations of design is looking into some potential landscaping options in that space in between the flood wall and that existing seawall. So that's just an example of something that would be looked at in the next phase of design. Next slide. And so making our way back to the southern end of the park to Collins Cove Beach, um, you can see that new flood wall terminates at that Collins Cove Beach access point where that potential deployable stop log um, structure would be. Um, and so you can see in this graphic there are the two locations where those access points would be maintained. Like I mentioned, it would likely be some sort of like seasonal or storm dependent type access. That's something that would also be determined during the next iterations of design. Um, but yeah, those are kind of the key highlights of these different um, plan view sections. Next slide. Um, so as I mentioned before, um, while most of what I've talked about up to this point is that new flood wall back behind the existing seawall, um, based on some of our structural analysis that we had done, um, some sections of the wall are in pretty good shape for the most part, and with some repair work, they could be maintained into the future and continue to serve um, the shoreline protection services that they were initially constructed for. Um, and so I'll just talk through some examples of what that repair work might look like to restore some of those sections of seawall that are in better shape to bring them to allow them to continue to serve to protect the park. Um, and so I have a couple images on this slide showing locations where there are crack on the left hand side of the screen where there's some cracks in the concrete uh, portion of the wall in front of the park. The city has actually repaired some of those sections previously, which you can actually see in this image where they injected some sort of polymer to fill those cracks and to prevent them from continuing to expand. Um, and then the images on the right show examples of where um, mortar has started to break off from in between the granite blocks. And so as part of the repair work, repointing of the mortar joints would be completed um, to continue to support those granite blocks and make sure that they don't fall out from the existing wall. Next slide. Um, Another part of the repair work, and this is kind of similar to restoring the mortar um, in between the granite blocks. If you walk along the wall, you'll notice that there's, especially during the summer, there's weeds growing in those joints in between the granite. Um, and so as part of that restoration process, those weeds would need to be removed prior to any repointing of the mortar and the joints. Um, Well, this isn't really a repair, but something I just wanted to note as it has to do with vegetation along the park. Um, if you walk along Collins Cove Beach, you can see um, marsh grasses along the beach areas, and I just wanted to be clear that those grasses are not weeds. They wouldn't be removed. They actually serve habitat and ecosystem um, services for the beach, and also, yeah, mitigate some erosion and um, reduce impacts of waves and currents from eroding the beach. So um, that's good vegetation that you know we want to maintain out there. And so I just want to be clear that will be kept, but the weeds that are breaking down the wall itself, that's what would be removed. Next slide. And the last type of repair that I'll talk about is more has to do with foundation. Um, in the upper right hand corner of the screen, you can see where um, foundation underneath those kind of like vertical um, concrete sections near the end of Connors Road. The foundation underneath them has broken and eroded and broken down. And so if that section of seawall was to remain, a new foundation would likely need to be restored because so that the structure doesn't become unstable during potential wave or storm impacts. Um, there's also other sections where the concrete footing has eroded back, and you can even see steel rebar exposed. So that would also be need to be repaired. And then on the left, if you've ever walked along the back, um, along the shoreline there at the back end of the existing seawall, you can see where the city has started to fill in sinkholes with gravel. And in those locations, um, sediment or dirt has eroded underneath the structure just due to all the voids and holes in the structure. And so those those locations would need to be restored as well. Next slide. And so that wraps up the coastal flooding aspect of like the analysis and the preliminary design that we looked at. Um, Towards the end of the presentation, I'll wrap things up with talking about the next steps. But before that point, I just wanted to um, talk about some of the stormwater flooding analysis that was done, and then how that informed the preliminary design work. Next slide. So before I talk about some of that analysis and preliminary design, I first wanted to talk about, what causes stormwater flooding in the first place. Um, and so, typically uh, when that stormwater flooding is happening, it's during a high intensity rainfall. So when a lot of rain is coming down in a very short duration of time, you can think of it kind of as this high intensity rainfall is happening during a summer thunderstorm. Um, and the flooding itself happens when there's not enough um, structures, so like catch basins, which are those like graded um, structures that you'll see along roads where um, the stormwater drains into. And if there's not enough of them, the stormwater can't flow into them sufficiently, and that water then ends up ponding on the streets. Um, Through those catch basins, there are also pipes that drain out through outfalls. And if those pipes are not large enough um, to handle the rate of stormwater from these high intensity storms, um, those pipes get backed up, and again, water will pond on the streets and in people's yards and eventually people's homes. Um, and so, yeah, as part of this analysis, we looked at, where could additional catch basins be included or pipes be increased to try to mitigate for that stormwater flooding. And one thing I just wanted to note is um, where stormwater ties into coastal flooding, and that's at these outfall locations, which you can see in the graphics on the right. Um, During low tide, it's easier for that stormwater to leave the system, um, as the water levels outside of the outfalls have dropped, so the water can exit through that pipe. Whereas at high tide, it makes it more difficult for that water to um, to leave the system, and so you'll typically notice that stormwater flooding is exacerbated or increased at high tide, but once the tide drops, um, the drainage infrastructure will have an easier time to release that water. Next slide. And so here are a couple pictures or examples of some locations in the neighborhood that typically tend to back up at these catch basins just due to undersized pipes, and where that flooding occurs. Next slide. So like I mentioned, we analyzed the existing infrastructure and the pipes in the neighborhood so that we could evaluate, where additional catch basins or um, pipes could be increased to better handle that flow out from the neighborhood and through the outfall, which you can see an example of one of them in the image on the screen. There are a couple other There are two other outfalls on in Collins Cove Beach, but they drain from a much smaller area. Um, and one such solution that I'll talk about is um, for improving the drainage in the system is to try to utilize some of those outfalls with some redundancy in the system. But um, so just as a starting point, this image here is showing where the pipes are that we looked at in the drainage area, um, and where we included them in a stormwater model. And if you want to learn more about that modeling and analysis work that we did, um, I'll, I think Neil mentioned that he was linking to um, some of the past presentations that we did where we talked about some of that um, modeling analysis, where you can learn more about what we looked at as part of the project. But I'll just be doing a high level overview of what we determined and how it informed um, some of those preliminary designs. Next slide. So just adding to that image, those blue arrows show the direction that the stormwater flows through the pipes to get um, through the out through the outfall. And so that was also something that was looked at um, as part of the modeling analysis. Um, and this just kind of showing these flow arrows highlights, that the majority of the stormwater system or the majority of the stormwater that's captured by the drainage infrastructure in the neighborhood all flows out through that stormwater outfall in the park. And just with all that water flowing out through that one outfall, um, when you get a high intensity rainfall like that summer thunderstorm, it can overwhelm the system and the outfall. Next slide. So like I mentioned, we looked at some possible locations where we can um, increase the pipe size as well as add new catch basins. And so you can see where some of those locations are. Those catch basin locations are in pink, um, and the increased stormwater pipe sizes are in purple. Um, and the orange lines show where new pipe could be installed to allow for um, redundancy in the system and routing some of that stormwater out through one of the outfalls in Collins Cove Beach. So it just gives the water another location or direction that it can flow to leave the system and not overwhelm the existing infrastructure. Next slide. Similar to before, those blue arrows just show where um, that stormwater is flowing, and the dark blue shows how by including or constructing some of these drainage infrastructure improvement projects can allow for more paths for that water to get out, leave the system, and drain through a different outfall in Collins Cove Beach. Next slide. And just to summarize with um, the modeling analysis that I talked about before, which again, you can watch one of the previous presentations to learn more about that modeling analysis. But we use the model to evaluate where stormwater flooding is happening during a future intense rainfall event. And that's shown in the modeling results on the left-hand side of the screen, where you have um, a maximum depth of stormwater of around 1 to 1.5 feet at the junction of Collins Street and Connors Road, near Lathrop and the junctions with Lathrop and Beacon as well. And the total flooded area for that future intense rainfall event without any constructed projects is around 3.3 acres of flooding. Where if we include those conceptual preliminary design projects that I discussed in the previous slide, it reduces the flooded area down to just 0.2 acres with a maximum depth of around 1/10 of a foot to half a foot in a very small location um, in um, in the neighborhood. And one thing I just want to mention, I just want to circle back to that distinguishing between low tide and high tide events. Um, these these results show what would happen if this rainfall was happening at low tide, when it's easier for the water to drain from the outfall and leave the system. Um, that would look differently at high tide, where temporarily, as the tide is up, that stormwater would likely pond. Um, there would be some ponding in the streets, but once the tide drops, it would allow for that water to get out. And so that would still happen with the constructed projects, but it would have an easier time to leave the system during that intense rainfall event. Next slide. And from there, I'll pass things off to my colleague, Ellen Douglas, who will talk about some groundwater analysis in the neighborhood.
Hi, everybody. I'm Ellen Douglas. I'm a project manager at AECOM. And in order to understand the role that groundwater plays in the flooding that has been experienced in Collins Cove neighborhood, we put in some monitoring wells back in November of 2025, and we put in some devices that measured the groundwater table and how it fluctuated over time. And so I wanted to show you the results of that. So next slide, please. So We installed 3 monitoring wells. Some of you may have noticed this out there last November, and also noticed people poking around in the ground about every week to every month between November and May of this year. So if you see the map on the right-hand side, you can see the location of the 3 wells. Monitoring well 1 is over on Connors Road. Monitoring well 2 is at the corner of Bridge Street and Lathrop. And monitoring well 3 is in front of the Collins Cove Park. And we installed what are called transducers that would measure the water level every 15 minutes and store that data. And then once a week, at once every couple of weeks, and recently once a month, we just went out and downloaded the data and then plotted it up and analyzed it. And I'll show you those results. And this just gave us a chance to really understand how deep the groundwater is, how it responded to rainfall events and snow melt events. And so yeah, go ahead and go to the next slide, please. Here is the plot that shows the groundwater level data that we collected. And I'll explain the 3 different well data are in 3 different colors. So the green plot that you see that's going along the middle of the graph, that's the MW2, which is at the corner of Bridge Street and Lathrop. And near the top of the graph, you can see a green dashed line, and that shows where the ground surface is. So the top of where the grass would be and where the sidewalk and the pavement would be is at that elevation of a little over 12 feet above sea level. And then the plot of the groundwater is the green jiggly line that you see that's running through the middle of the plot. And then the other 2 wells, MW1 and MW3, are lower on the graph. The orange is the MW1, and that's the one on Connors Road. And the blue is MW3, which is in front of the park. And you can, not surprisingly, since those 2 wells, MW1 and MW3, are very similarly located relative to the Cove, the groundwater elevation there is very similar. They respond slightly differently, but generally respond in a similar way. And the one up on the corner of Bridge Street in Lathrop responds a little bit more, and it's at a little higher elevation simply because the ground surface is a higher elevation. And the other blue triangles that you see in the plot are daily precipitation events. So in general, most of the precipitation that falls in the area is half an inch or less, but we did get a few events that were at 1 inch or more. And the jiggly lines that you see are the responses of the groundwater to those events. So if you go to the next slide, just to summarize some of the things that we found, the average depths of the groundwater at these locations were between 4.5 and a little over 5 feet below the ground surface. The deepest depths were about 5.5 to 6 feet, and the shallowest depths, meaning when the groundwater was closest, was between 2.5 and 4 feet. Oh, if you could go back one slide just for a second. You can see where the groundwater increases in early March. That is in response to some rain events and some snow melt. So the groundwater got closest to the ground surface, not surprisingly, during those times when the ground finally thawed and allowed water to infiltrate, and rainwater and snow melt to infiltrate into the ground and recharge the groundwater, and that made the groundwater increase towards the ground surface. But then as that snow melt pulse reduced over time, you can see that the groundwater level has receded back to its normal between 4 and 5 feet depth. So go forward again, please. And then if you click once, I animated this. So in general, the water, what was a little surprising to me, but I guess not all that surprising, knowing that the subsurface, the ground underneath your neighborhood has clay and a lot of fine materials. The water table fluctuations were not directly linked to the tides right now. So over time, groundwater will rise as sea level rises, but we didn't see a big signal, a tidal signal in the groundwater levels. Click again. On average, as I said, the water table stays about 4 to 5 feet below ground surface, but some of you who have basements probably notice that in the spring, especially, you may, if you have sump pumps, your sump pumps may be running more than they normally do, simply because the snow melt and spring rainfalls are adding more water to the groundwater and causing the groundwater to infiltrate into your basements. Click again, please. So yeah, as I said, groundwater is higher in the spring as the snow melt and lower in the fall. Click again. Oh, so these are just the Spanish translations of what I said. So in general, we didn't find anything surprising. It was pretty much what we would expect. And during the time that we monitored the groundwater from late November of 2025 through the end of May 2026, we did not find any times where the groundwater actually reached the ground surface, which and caused direct flooding. But certainly, as I said, if you had basements or anything that was below the surface, it might be impacted by groundwater at certain times of the year. The other thing I wanted to make sure that we mention as during this time that we were monitoring the groundwater, we have been in drought conditions since last summer, and we still remain in fairly substantial drought conditions. And so if we were to monitor groundwater in another year where the precipitation was higher and we weren't in the drought, the groundwater levels might be different. I think that's all I had on the slides for the groundwater. So Matt
All right.
or Neil?
Yeah, I'm jumping in first just to wrap up coastal flooding and stormwater flooding. But before I get into that, I saw we had one question in the chat that was answered just about the wall height and the fact that 2 to 4 foot range is a big range. I just want to be clear. We have a sense of what the elevation of the wall would be, the top elevation, and that would be set at a design flood elevation. So right now um, we have a planned design elevation for the wall, and the reason for the 2 to 4 foot fluctuation is it just depends on what the existing ground elevation is along each section of park. Um, so, for example, the actual elevation of the park itself varies by around by a foot or two, with some high points and some low points. The lower points, you're going to need closer to 4 feet to reach that design flood elevation, whereas the higher points of the park, you just might only need 2 or 2.5 feet of concrete wall to reach that design flood elevation. So I hope that clears things up just in terms of what that wall elevation would be. We know what it would be, but it just depends how tall it actually is depending on where you are in the park relative to the existing ground. So with that clarified, I'll jump into wrapping things up. Next slide. So before we get into progressing for the next phase of the project, from progressing from these preliminary designs to a 100% or final design, there needs to be some more technical investigations to evaluate what conditions there are to properly design the wall to deal with those conditions. And some of those investigations include soils of the surveys of the soil to see what and how we can build on it. For example, on the image on the right is an example of a drilling rig to take soil borings, which would give us a sense of the condition of those soils. If you were at the park, I think last Friday, you might have noticed something like this that actually, or a rig like this, which was actually taking some soil samples at a couple locations in the park. So there'd be more analysis like that, as well as some analysis of sand movement and waves in the cove to make sure we're not having any negative impacts with wave reflection. And then more from us for the stormwater projects, we would need to further survey elevations of the road and utilities before constructing any drainage improvements. Next slide. And so those investigations will help with progressing that future design from the preliminary conceptual design that we talked about in this presentation as part of this project to get it to that final design. And so as part of that design process, we'll need to look at construction impacts, for example, costs of the project, scheduling and sequencing. That applies to both the coastal flooding preliminary designs as well as the stormwater flooding designs. And something not mentioned here is also permitting and submitting these designs to regulatory agencies to make sure that they meet all of those criteria. So that's just a summary of some of the things that would be looked at as part of the next stages of the design. Next slide. I think with that, I'll pass things off to Neil, who will wrap things up.
Yeah, thanks, Matt and Ellen for all the great information and work on this. So for the next steps, I mean, the next immediate steps is we're finalizing this project, which officially this grant period ends at the end of June. So we'll be, finalizing all the reports from AECOM, making those available on the public input site in order to do some of those investigations and find out more information needed to advance the design. As Matt mentioned, we will be seeking additional funding. The best known source of that is the source that we've been using for this grant and the previous grant, which is the state funding programs through the Executive Office of Energy and Environmental Affairs. Their grant process is likely to be in the sort of late winter, spring timeframe of next year. So we'd be looking at that, certainly be looking at that as a potential source to advance the design and the work and possibly the permitting of the coastal project, as well as there's a seawall repair program as well that we'd be looking into potentially to try to do some of the repair work mentioned. And we'll be weighing these projects with other projects in the city. The stormwater projects are a little bit different in terms of we need to continue to share this information with our engineering department and Department of Public Services, and have a better understanding of what the priority projects are citywide and try to see how best we can coordinate some of the proposed work with potentially with projects that may be happening in the area. as well as to do some of that surveying that Matt had mentioned, to understand more about the stormwater system, potentially doing some like um, closed caption camera surveys of the stormwater infrastructure. Um, so I think that's all for next steps. I think the next slide is just about questions. If there are any additional questions, please type them in the Q&A. And we have a public input site, as mentioned. The QR code and URL are on this last slide here. This recording, as well as previous recordings that Matt had mentioned that have occurred over the last 2 years, are on that site, as well as project documentation. So please check out the public input site. And you can always reach out to either to me in the Sustainability and Resiliency Department, as well as Barbara Warren. Yeah, Matt.
Yeah, I just, you always remember something
Yeah, of
after.
course.
Want one thing I just wanted to add as part of the future design considerations. I know we mentioned it during the presentation, but just wanted to reiterate that, you know, during that progression from the preliminary design to 100% design, the project team will continue to engage you guys, the community, just to get feedback, see, what sort of amenities and considerations can be incorporated in the project just to, better serve the people that are using the park. So, yeah,
Yeah, no,
I
thanks
missed
for
that and just
thanks
wanted
for
to
emphasizing that,
highlight
Matt. I
that. Yeah.
appreciate it. Yeah, that we're definitely, when we get into more of the details, a lot of those details are the things that really matter to people in terms of the use of the space. And so, yeah, we certainly will continue the engagement going forward. And it's been great. The walk and talks and the meetings thus far, we've gotten really, really good feedback from people who live in the area are impacted by these events. So we're looking forward to continuing that, continuing that process. Um, Not seeing any questions. Thanks for attending and for your interest in the project. And we look forward to continuing the process going forward. Thanks, Matt and Ellen, for all the great information. Have a good night.